Okay, hello everyone, and it's my pleasure to host our seminar speaker today, Indujaa Ganesh, here. She's a research assistant professor at the University of Alaska Fairbanks Geological Institute. She did her, in the early days, she did her master thesis at the Indian Institute of Technology in Bombay on layered deposits in Valles Marineris on Mars. And she had a PhD in planetary science at the University of Arizona, investigating explosive volcanism at Mars and at Venus. She is the recipient of the Amelia Earhart Fellowship, and she is now working on volcanism, but not only on Venus, but also on Mars, on Earth, and at the Moon, especially by using microwave remote sensors. She's a science team member for the VENSAR instrument, which is a radar, a microwave radar, on the Envision mission from the European Space Agency. And today she's going to present Volcanism on Venus, tools for studying past and potentially ongoing activity. Welcome to Indujaa.
Thank you. Thanks, Cyril. I hope people can hear me okay. Let me know if not. Things are good on Zoom, I guess. All right. I'm really excited to be here today. I was telling Cyril this earlier. A lot of my friends from grad school were originally from the Jackson School. They were at UTIG and Jackson School and then moved to Arizona. So I've heard a lot of good things. So it's nice to finally be here and check things out in person. So my goal for the talk today is just to get people thinking about and hopefully interested in volcanology, but specific to Venus, right? So Venus is a really cool place to be studying volcanoes, if that's something you're interested in. But as we will see in the talk, studying anything on the surface of Venus, including volcanic landforms, is quite challenging. So as a result, there's still a lot of questions that we don't understand about how volcanic processes work and modify the surface of Venus. So my plan for the talk today is to highlight some of these big unknowns, highlight some of these big picture questions that we're trying to answer, and then go into some of the work that I've done in the past and some of the work that I'm currently doing towards addressing these questions. And then in the very end, take a couple of minutes to talk a little bit about what we, and when I say we, I mean the Earth and planetary science community, what we as a community can do to keep pushing the field forward. And before I go into the talk, I wanted to give a quick shout out to all the collaborators that I have listed on there. Some of these are my advisors from grad school, and some of these are students that I worked with, and the rest are people that I'm currently working with as a part of the VENSAR science team. Okay, so we have two planets, right? They're Earth and Venus, very similar in terms of their size, very similar in terms of their bulk silicate composition, but that's kind of where the similarities end today. So I mentioned that the surface of Venus is quite challenging to study, and that's because of two reasons. One, the atmosphere of Venus is optically opaque. The atmosphere, unlike Earth's, is rich in carbon dioxide, and it's about 75 times as dense as the atmosphere we have on Earth. And about 50 to 70 kilometers above the surface, there's this really thick layer of sulfuric acid clouds, which means that if we tried pointing a camera, either from orbit or if we tried pointing optical telescopes on Earth towards Venus, all we would see is something like that, which is the atmosphere and not the surface. And the other reason studying the surface is really difficult is because of the high temperature and pressure conditions on the surface of Venus. So the surface temperature is about 740 Kelvin. For comparison, Earth's surface temperature is about 300 Kelvin. And the surface pressure is equivalent to standing about 1 kilometer under Earth's oceans today. And we currently don't have the type of technology to be able to perform any type of long duration surface science activities on Venus as a result. Now, how then do we study the surface of Venus? We've done this in a couple of different ways. One is through short duration surface activities. So by that, I mean a few landers that have visited the surface of Venus back in the 60s. These were the Vega and the Venera landers, and they provided the first and what remains till date, the last ever photographs of the surface. Those are shown on the left-hand side. In addition to these photographs, at 7 different locations on the planet, these landers also measured the surface composition, either through gamma ray spectroscopy or X-ray fluorescence. And what they found was that the composition was dominantly tholeiitic basalts or ocean island basalts. So the surface of Venus is very similar to what's formed on Earth by seafloor volcanism, right? And these photographs and this compositional measurement together was sort of the first confirmation that the surface of Venus, at least in these 7 places, is primarily volcanic in origin and very similar to what we might find on Earth's seafloor. So the second way we can study the surface of Venus is through longer wavelength remote sensing. So not optical, but longer wavelengths than that. The atmosphere has a few windows in the infrared region. So the Venus Express mission that I put a photo of on the, well, an artist's illustration photo of on the bottom right there is an ESA mission that visited Venus in the sometime in the 2010 decade. And they used infrared spectrometers to look at the surface of Venus. But mostly, a lot of the data that we use for Venus's surface primarily comes from even longer wavelength microwave or radar remote sensing. Right? This includes a bunch of radio telescopes on the Earth that we've used to look at the surface, ranging from 3 centimeters to almost 70 centimeter wavelength. This also includes a few orbiter synthetic aperture radar missions, or SAR missions. There's Pioneer Venus, which was NASA's first SAR mission back in the 80s. And the one that I'm going to highlight is at the bottom center there, the Magellan mission, which was NASA's last SAR mission to Venus. It was in the early 90s. The spacecraft carried a 12.6 centimeter wavelength SAR instrument. So this is an S-band radar. And most of the data that all of the surface scientists that study Venus's surface use today comes from this mission. And also a lot of the photos of the surface that I'm going to show throughout the rest of the talk is from this mission. So there are a lot of cool findings that came out of Magellan, right? And I want to highlight 2 of those. One is the diversity in volcanic morphology that we see on the surface. Starting from up top, we see lava flows that are hundreds of kilometers long. And then we see sort of this pockmarked surface texture here, which has been interpreted as clusters of shield volcanoes. So both lava flows and shields are, very classic morphology that we would expect with basaltic lava. Cool. But then we also see a lot of things that don't seem very consistent with basaltic lava. So on the bottom right there, the circular features that you're seeing are called pancake domes, and they're thought to be similar to lava domes on Earth. And forming lava domes requires a lava rheology that's usually a lot more viscous than just basaltic lava. And in contrast to that, we also see really long lava channels. The photo on the bottom center is an example of a lava channel that's almost 1,000 kilometers long. And to form something like that, we need lava that's a lot less viscous than basaltic lava flows. And then we also see some really high backscatter deposits that are shown on the bottom left here that are interpreted to be ash deposits or tephra deposits or pyroclastic deposits, which is also not something that we would commonly expect out of basaltic volcanism. And I'm going to, for the good majority of the talk, we will be talking about these proposed pyroclastic deposits, so I will come back to this in a little bit. But the main point that I want to make in this slide is that we're seeing how the basaltic composition that we know of from just 7 different places on the surface is already proving to be inadequate to explain this diversity in morphology that we see in the remote sensing data. And the other main finding that came out of the Magellan mission that I want to highlight is the distribution of impact craters on the surface. So typically in planetary science, we use the size and spatial distribution of impact craters to relatively age date the surface. So any surface that has a larger number of impact craters or has larger impact craters are typically considered to be older than another surface on the same planet that has lesser impact craters or smaller impact craters. And on Venus, we have a grand total of only 1,000 impact craters. This is an order of magnitude lesser than what we would see on the Moon. And it's indicating that the surface is pretty young. And what's more puzzling is that when we look at the size distribution of these craters, it's a pretty random distribution. And that's telling us that no place on the surface of Venus is statistically significantly older or younger than any other place on the surface. So what we have is a surface that looks like it's uniform in age everywhere and also pretty young, right? And one of the very first theories that was put forth to explain why this might be is it's called the catastrophic resurfacing theory. And the idea here was that when volcanism does happen on Venus, it happens in really copious amounts, pretty much everywhere on the planet, all at the same time, that the entire surface is covered in new lava in a very small duration of time, making it look like the surface has the same age everywhere. Another hypothesis that sort of came a little bit after is the equilibrium resurfacing hypothesis, which suggests that Venus might have Earth-like levels of activity and still look the way it does. So this theory says that we can produce the same type of random distribution of impact craters by having more small levels of volcanism that are randomly distributed in both time and in space. And then the cool thing about this theory is that if this is in fact what's going on Venus, then we have another planet that is very Earth-like in terms of its volcanic activity levels. Right, and I think it's safe in saying that a lot of the community today is starting to lean towards the equilibrium resurfacing theory, even though the catastrophic resurfacing was where we initially started in the 90s. And the reason for this is that in the past decade or a couple of decades, there's been a lot of new studies showing that the surface of Venus might, that Venus might actually be volcanically active at timescales that are observable today. So this is a really nice graphic from ESA where they highlighted some of the results from the Venus Express, which was an infrared mission showing some of the studies that came out in the aftermath, pointing that Venus might be volcanically active. So I want to draw attention to the graph on the top there. This is temporal variations in sulfur dioxide from pioneer Venus times in the 80s till Venus Express times in the 2010s. And Mark et al. In 2012 pointed out that this temporal trend is possibly best explained by new injection of sulfur dioxide into the atmosphere, possibly by volcanism. And then a couple of other studies looked at infrared emissivity of the surface. So this is an example here where they looked at the infrared emissivity of some of the volcanic summits on Venus and saw that these places have higher infrared emissivity and, compared to the rest of the planet, suggesting that they might have fresh, young, unweathered basalts that might be only as old as a few tens of thousands of years. Now, these are mostly considered kind of indirect circumferential evidence for Venus being volcanically active, right? What is considered more quote unquote direct evidence for volcanic activity actually came out earlier this year. This is a paper by Herrick and Hensley in 2023 that used change detection methods using SAR imagery to point out that Venus might be volcanically active and that the Magellan mission might have actually observed an eruption while it was there. So what we're looking at in this figure are SAR backscatter images of a location that's pretty close to the summit of this volcano called Mat Mons. And the image on top, right panel, is data that was acquired earlier in the mission, and the image on the bottom right is data that was acquired later in the mission. And what the authors point out that circular vent here, right here, yeah. A volcanic vent that was circular and earlier in the data has changed shape and looks more kidney bean-like in the later part. And they point out that this big of a surface change is possible only if this place was volcanically active. You know, smaller localized mass wasting processes can't possibly explain this big of a difference in the surface. Now, you know, if you try and summarize what we've learned about Venus volcanism back from the Vega and the Venera landers in the 60s, up to this idea that Venus might be volcanically active and possibly direct evidence for that in 2023. What we know is that we have a surface that's primarily dominated by basaltic volcanic activity in most places. And some of these volcanoes might actually be active at observable timescales today, right? But that also leaves us with a lot of unknowns. For instance, if Venus is volcanically active, what is the current rate of volcanism? You know, is it similar to Earth? Is it slightly different or really different from Earth? How has that changed over Venus's history? We also don't understand a lot about the different types of eruption styles and how they contribute to surface modification on Venus. For example, on Earth, the two common volcanic eruption products are lava flows and ash, and the relative volumes of these products vary from volcano to volcano, vary from year to year, from geodynamic setting to setting. And they tell us a lot about not just modification of the surface, but also long-term volcanic evolution. So being able to do something like that for Venus would also be super cool. We also don't know much about the composition. We saw that so far the measured composition is all basaltic, but we also know that the geomorphology indicates a larger variety in composition that we don't understand. And that can tell us a little bit more about melt production and magma migration. So which part of the mantle is being melted to produce all this magma? Is it directly sourced from the mantle? Are there crustal reservoirs? If Venus is volcanically active today, does that mean there's a layer of melt somewhere in the subsurface? And finally, again, if Venus is active today, what is the rate of volcanic outgassing? So we have a really dense, thick atmosphere that is primarily volcanic in origin. How fast or how often is this atmosphere being replenished by volcanic activity on Venus? So these are some of the main big picture questions that I was saying we still don't really understand the answers to, and we're trying to understand the answers to. And I want to pick two of these questions and talk about them a little more in detail today. So the first one is talking about eruption styles and contribution to surface modification, right? So for this, I want to go back and talk a little bit about some of the work that I did during grad school, trying to think about explosive volcanism on Venus and how that modifies Venus's surface. And the second question that I want to talk about is the one on top, which is current and past rates of volcanism. So how do we, what are some strategies for understanding if Venus is active today? And if so, then estimate what the level of activity might be. And then at the very end, just for a few minutes, I want to talk a little bit about where do we go from here to keep pushing the field forward. Does anyone have any questions or something like that? Any small questions on anything on Zoom? No? Okay. So getting into part one, which is thinking about explosive activity on Venus and what its contribution might be. All right, so explosive volcanism, when we think about it, it's not really prevalent outside of Earth in the solar system, but it gets disproportionate interest and attention because typically what determines whether an eruption is going to be effusive or explosive in nature is how saturated the magma is in volatiles, right? If you have a magma that's very saturated in volatiles like water, we end up getting explosive eruptions like shown on the right-hand side there. So typically, explosive eruptions are telling us that the melt being extruded out is rich in water, which also means the subsurface that's being melted to form this magma could also be rich in water. And that tells us something about the water content in the subsurface of other planets. So typically, even though it's not prevalent on other planets, it still gets a lot of attention, and we're interested in this question purely for the purpose of thinking about water in the subsurface, right? And just try to show a difference between like effusive and explosive activity, just in case people, it's not something people are familiar with. And I want to point out one thing here. With explosive activity, you know, when we think about these tall eruption columns and sort of textbook style volcanoes, what we're talking about is typically explosive activity where all of the magma is kind of broken up and thrown out of the ground with lots of energy and velocity. And we often end up with tall ash columns like that. And that's going to be a little relevant for later in the talk. So there are places on Venus where people have proposed that there might be pyroclastic deposits or ash deposits. And I've shown a couple of examples on the left-hand side here. So that's the deposits that are marked with a yellow outline. Those are examples of places that people think there might be pyroclastic deposits. And the reason these are classified as such is because they occur at volcanic structures, but they don't look anything like lava flows that we see elsewhere on Venus. So for an example of a lava flow is there on the right-hand side. And if you look at the lava flow, so if you look at the lava flow, we see a bunch of interior flow units, we see different surface structures. But then when you look at the pyroclastic deposits, it's just this diffuse glob. We don't really see any interior structure. And then the lava flow has also very clearly defined margins. The proposed pyroclastic units do not. They sort of have a diffuse appearance in the SAR data. And a couple of other important things to note are that these deposits are really big. So they extend for nearly hundreds of kilometers. That's kind of clear from the scale bar. And in a lot of places, they are seen burying lava flows, like pointed out on the top left there. So it's been suggested that these deposits probably represent a younger episode of volcanic activity on Venus that was more volatile-rich and primarily different from any previous lava flow forming activity. And as for the main hypothesis of how this deposit forms, every single study that has looked at this deposit has so far suggested that these deposits form via pyroclastic flows or pyroclastic density currents. So one of the ways to get this is the tall ash column that we saw. if that column cannot be sustained for a long period of time, it can collapse, feeding this really fast-moving mixture of hot fragmented magma and gases and entrained air. There's an example from Tungurahua volcano, and you can also see a deposit formed by PDC in the forefront of that volcano right here. And the prevailing hypothesis is that these deposits are formed by pyroclastic flows on Venus. And the people that have studied this in a little more quantitative manner have showed that in order to get explosive eruptions, you need about 2 to 6 weight% water in the magma, which is towards the upper limits of what we do find on Earth, but it is not outside the bounds of what we find on Earth. People have also studied what happens to the eruption column that forms on Venus. There's a bunch of studies from the 90s that talks about column stability on Venus. But something that was missing in the literature that we really did not understand was, well, what happens once this column collapses and forms a pyroclastic flow? So that's kind of what we were interested in. Once you have a pyroclastic flow on Venus, how does it transport material? How does it deposit material on the surface? And can it lead to these really big deposits that we're seeing in the data today? So we sort of divided that up into 2 questions. One was just trying to understand the transportation mechanics of PDCs. How do they transport material across long distances? And what eruption conditions would be needed to do that? And the second part of the question was, can we use the different data sets that we have of these deposits to try and understand what their surface properties might be, and use that to say something about the eruption conditions? So I'll go on to question 1 first. So this is where we modeled pyroclastic flows on the surface of Venus to understand how they transport material. The model itself was very straightforward. We assume that the PDC is a 2-component mixture. So you have some solids that are dispersed in a background fluid. And the whole thing is propelled forward by gravity and topography. The resistance to the flow comes from friction at the base of the flow, friction within the particles in the flow, and also any viscous drag. And if any of you are familiar with a bunch of USGS hazard management tools, like models like Titan 2D or WalkFlow, this is very, very similar in terms of the whole framework. But what's different is that it's set up so that you can plug in Venus gravity, Venus topography, and also it can handle a couple of different types of PDC initiation mechanisms. One was the column collapse that we talked about. The other is this idea of PDC formation by boiling over. And that typically refers to having a column that's kind of short, but long-lived in activity so that it keeps feeding a PDC for long periods of time. Now, I'll quickly step through what we learned from this. Sort of the first thing we realized was that it is really hard to produce such large deposits on Venus, right? It's not possible to have a single eruption or a single vent and still form a deposit that is hundreds of kilometers long. So in order to have formed these deposits at PDCs, we should have had multiple eruptions from multiple sources that are distributed in both space and time. The second main finding was that in order to form these deposits, we needed really large volume eruption rates. So what I mean by that is, in order to form deposits that are so big, we need a lot of volume of material to form these deposits. And first, that might seem like a no-brainer, but it's really interesting here because so far these deposits have been thought of very thin deposits, right? So centimeters to tens of centimeters thick. So ideally, their ratio of thickness to runout is pretty low. But what we find is that you can't form such thin deposits. You can't form deposits with a low thickness to runout ratio on Venus unless you have very high energy explosive eruptions. And that's not something we would expect on Venus today. But I'm not going to go into why, but I'm happy to answer questions about it later. But when you do have low energy eruptions, ultimately the deposits that do form end up being a lot thicker. They're anywhere between meters to tens of meters thick. As a result, you need a lot of volume of material to produce these deposits. And even then, when we did this for a variety of places on Venus, there were places where we weren't really able to match the extent of the deposit through our models. And the sort of the final takeaway here is that any pyroclastic flow on Venus, if it is going to transport material across long distances, needs to be fluidized. It needs to be highly fluidized. And if we think about why that is for a second, on Earth today, where we find PDCs are on the flanks of really steep composite volcanoes, right? And here, the steep topography helps accelerate the flow and makes it flow further and longer. However, on Venus, we're dealing with volcanic landforms that are primarily made of basaltic lava, which means we're dealing with topographic slopes that are anywhere between 1 to 2 degrees or even lesser. So in this case, the topography doesn't really do anything to help the flow. There is no acceleration induced by topography here. So the flow needs to start out with the velocity and fluidization that's high enough to be able to make it flow for nearly 100 kilometers. And we were able to recreate this by assuming very high pore pressure in the interstitial fluid. And that's because this has been reproduced in flume experiments. It's been observed in the field, but it's quite possible that there might also be other fluidization mechanisms at work. So the big takeaway from this was that if these deposits that we're seeing are indeed tephra deposits, and if they're formed by PDCs, then it's only under very narrow conditions that we can form them. We need very high volume eruption rates, we need multiple eruptions, and we need PDCs that have high interstitial pore pressure or some other mechanism of being fluidized for long distances. The second question we were trying to answer was, can we learn something about the properties of these deposits from the radar data, and then use that to think about how they might have been emplaced? So to go into this, I want to go back and talk a little bit about the radar characteristics of these deposits. So we already looked at the SAR backscatter data, right? That's shown on the left-hand side panel here. And you can see that these deposits outlined in white kind of have they look brighter than the surroundings, implying that they have higher backscatter than average. And we also looked at the microwave radiometry data. So the Magellan mission collected both active and passive microwave data. And the passive data are basically collected by you turning the transmitter off and just receiving any emission that's recorded at the antenna. And the microwave emissivity observations that are produced from the radiometry show that the deposits don't really have any, super high or super low values. They kind of look very similar to the background. So their emissivity values are only moderate. So we're looking at deposits that have high backscatter, but kind of only moderate emissivity values. But the one cool thing about these deposits that I want to point out is that a lot of these are present near, on the right-hand panel, a lot of these are present near these pinkish yellow regions. And these are regions of unusually low emissivity. So I'm not sure if the legend is super clear, but these are locations with emissivity value under 0.5. Which is not common at all for any geologic medium, right? And it's been suggested that it's because these are locations on Venus where there might be high concentrations of ferroelectric minerals or some kind of metal sulfides or metal oxides that are covering the surface there. Again, it's a super cool topic, but something that I'm not going to go into this talk. Again, happy to answer questions if people have questions regarding that. So the other type of constraint we have from the Magellan data with observations at different incidence geometries. I'm sorry, the text is over the image there. I didn't notice that. But during the time that Magellan collected data, I did that over multiple cycles, and these different cycles have different incidence geometry. So cycle 1 data was collected at a larger incidence angle than cycle 3 data. And you can see, even between these 2 cycles, you can see differences in the backscatter properties of different regions there. So kind of putting together the different backscatter and the emissivity observations and the different incidents, the goal was, can we then use backscatter and emission modeling to try and get back at some of the surface properties? So what we ended up doing was treating the pyroclastic deposit as 3 possible cases of surface and subsurface structure. In case 1, we assume that all of the radar signal that we're getting back from the deposit is primarily just from the surface. By that, I mean the atmosphere surface boundary. In cases 2 and 3, we assume that the signal that we're getting back is not just from the surface, but also possibly from the subsurface, which is absolutely possible if you're dealing with low density deposits, which are conducive for radar signal penetration to the subsurface. And the difference here between case 2 and case 3 is that in case 2, we assume most of the backscatter is coming from a continuous interface in the subsurface. In case 3, we're assuming that most of the scattering might be coming from distributed scatters in the subsurface. And we used a combination of a surface scattering model plus a vector radiative transfer approach to then compute what the expected backscatter and emissivity from these different types of structures would be, and compare that to the data. And I'm not going to go into every one of these cases. I'm just going to go into case 1 here, because for a variety of reasons, we decided that was probably the best explanation for what's going on in the data. So what we find with a simple surface scattering model is that, number 1, we need high amount of surface roughness. Right? We need moderate to even much higher amounts of surface roughness to be able to get the observed backscatter and emissivity. But what surprised us was on top of the high roughness, we also needed relatively high dielectric permittivity values to be able to get the observed backscatter. So permittivity is more of an esoteric quantity. We can use some empirical relations to convert that into density. And if we think about what that density translates to, it's about 2.4 to 2.9 grams per centimeter cube, which again, it's pretty dense for ash deposit or for a tephra deposit. This is getting close to having, close to what you would start expecting for lava flows, right? And I must point out, so we don't even know if these relations for converting from permittivity to density are valid for Venus. These are empirical relations that have been derived. I don't know how well these hold up when thinking about these unusual metal minerals on the surface and such. But I think the point still remains that we're seeing higher values than what one would typically expect for tephra deposits. So what does that mean? There are a couple of ways to interpret this, right? One, maybe these are not tephra deposits. Maybe these are just lava flows that have unusually high macroporosity, which gives us this permittivity value. Or another interpretation, the one we ended up favoring finally, is that these might be pyroclastic deposits, but for some reason they have higher density than usual. And we do see that on Earth. We see that with pyroclastic flow deposits that are welded. So welding is typically a process that can arise when the temperatures in the pyroclastic flow are high enough during emplacement that the different ash particles can fuse together, thereby expelling the pore spaces and increasing the bulk density of the whole deposit. So this could, if these are pyroclastic deposits, then welding could potentially explain why these deposits do have high density. And we're not the first people to suggest this. This has already been suggested before. Head and Wilson in 1986 suggested that there are welded pyroclastics on Venus, but at a more local scale and not for deposits that are hundreds of kilometers long. And Gale and Wilson in 2015 suggested something similar. And they also suggested there are welded pyroclastic deposits on Earth, but they suggested that at different locations. So kind of given that there's already evidence in the literature that there might be welded tephra on Venus, we kind of ended up going with the second interpretation here. So if we put together both these questions and try to understand, well, how do these deposits get emplaced by pyroclastic flows, we find that one, we need multiple eruptions that total up to a high amount of material being erupted out. And the PDC that forms from these eruptions would need to have high degree of fluidization, and it would need to have high enough temperature for material to weld together, and it needs to maintain that temperature for long enough periods of time till the whole deposit is emplaced. Now, if we pause for a minute and think about, well, is this actually possible? Can something like this happen? This is something we see on Earth, and the answer is absolutely yes. We do see a lot of welded ignimbrites and welded ash flow tufts on Earth. But the catch here is that we typically see that with large silicic caldera forming eruptions, right? We don't see this type of behavior in basaltic lavas on Earth. Which then raises the question, how does this happen on Venus? Can those really large explosive eruptions happen on Venus? If so, is that happening with silicic magma, or is that still happening with mafic magma? What types of volatile contents would we need in order to get that? And if we're finding such really large tephra deposits, does that mean there are also smaller deposits that might be more similar to what we see on Earth today in eruptions that happen today? And if so, are we not seeing them just because we don't have the right type of resolution of data? So these are still some questions, and I'm going to pause here and come back and talk a little bit about how do we go answering these questions at the end of the talk. But I'm going to switch gears and talk about detecting current activity and estimating current levels of volcanism at this point. And I'm pausing to see if anyone else has any other quick questions before I move on. Okay. All right, so this is a really interesting problem, right? And it's also a very timely problem because there are a lot of missions that are going to Venus, or hopefully plan to go to Venus, and they will go to Venus. This includes an orbiter from China that's mostly going to focus on the climate. An orbiter from India that if I remember right, is primarily a synthetic aperture radar mission. And there's the NASA Veritas mission shown on the right top, and then there's ESIS and Vision missions shown on the bottom right. They're both synthetic aperture radar missions. NASA has another probe mission called Da Vinci, which is scheduled for launch in 2029. And then there's a private mission by Rocket Labs called the Venus Lifefinder mission, which is being led out of a science team based out of MIT. So we have numerous missions going to Venus. And at least for the two SAR missions that I'm familiar with, which are the NASA Veritas and the ESA Ambition, one of the many mission science objectives and requirements is to detect any ongoing volcanism on Venus, right? And they both have instruments capable of doing this. They're both going to have synthetic aperture radars on board. The one on Veritas will be an X-band radar. The one on Ambition will be an S-band radar. They both have the same set of they both have the same spectrometer being built out of the same lab in Germany, so similar capabilities for that. And they're going to employ a few different techniques for trying to detect volcanism. So one is repeat imaging. This is what we saw earlier with the Herrick and Hensley paper. So these missions are scheduled for launch in the early 30s, and then they would get to Venus maybe 2 to 4 years from then. And that gives us nearly a 40-year-long temporal baseline between when Magellan collected data off the surface and when these missions will collect data off the surface. And even between these two missions, there's a little bit. There will be a little bit of overlap if they stick to the current schedule and launch as planned. And there will also be a shorter baseline between those two, shorter temporal baseline between those two missions. So that gives us two different sets of temporal baseline to look for volcanic activity. And there's a new paper. I wanted to highlight this paper by Campbell and Hensley for people that might be wondering, well, the wavelengths for these different SAR instruments are very different. How is that going to impact change detection? That's something people are still working towards, but one of the initial papers just came out with some strategies for doing that. So if that's something that people are interested in, they should definitely look that up. The second technique that both of these instruments will employ is infrared spectroscopy. So they will look for thermal anomalies on the surface associated with active lava flows or any other type of volcanic activity. And additionally, the Envision mission will also look for increased concentration of volcanic species in the atmosphere using the spectrometer. And the third strategy, the one that I'm going to talk a little bit about today, is something only the Envision mission will employ, because that's the only, between the two SAR instruments, only the Envision instrument is planned to be operated in the passive mode. And in the passive mode, Envision will use its SAR instrument to look for thermal anomalies, not in the subsurface, but in the subsurface. I'm sorry, not in the surface, but in the subsurface. And this is theoretically, this should be useful for detecting things like lava flows and lava lakes. And this is sort of the concept behind it, right? So when we have a lava flow emplaced on a surface, it starts cooling by a few different heat loss mechanisms. You start conducting heat out of the bottom of the lava flow into the ground, so that cools the bottom. We start losing heat through convection and radiation on top, which forms a crust that then starts thickening via conduction. Now, what this ends up doing is it ends up insulating the core of a lava flow, since the bottom and the top have cooled and it's no longer directly exposed to the atmosphere. And this insulated core will lose heat slower and therefore can stay hot for extended periods of time. So the plot on the right is showing a few different temperature profiles of 1D temperature profiles through a lava flow for several days, from 100 to nearly 1,500 days after emplacement. And the idea is that because radio waves are capable of penetrating deeper than infrared, any temperature anomaly in the subsurface should ideally show up in the passive radiometry data. And what I am interested is in understanding how ages and the composition and the different cooling mechanisms of lava flow ultimately impact what we might see in the brightness temperature data. So what I'm showing here is basically temperature profiles for lava flows from a couple of hours to nearly a year after their emplacement, just for the upper 1.5 meters, right? And then on the right-hand side, I'm showing what the expected radiothermal emission would be in terms of brightness temperature for all those different ages of flows. And the gray box there basically shows the mean plus or minus 3 sigma limits of brightness temperature that was measured by the Magellan mission. So theoretically, for a minute, if we ignore things like the area of the flow and simply think about temperature, this is a concept that should work, since flows that are even up to a year old have brightness temperature values that are well above what we would expect for the background and what was measured throughout the Magellan mission. And another cool thing about this is, if we collect radiometry data at this and see something interesting at the same time as we also see something interesting in the infrared data and also in the SAR data, then having these different types of data sets then provides us the ability to not just monitor or detect volcanic activity, but also think back about what some of the properties of the lava that's being erupted out is. So for instance, different types of lava compositions erupt out at different temperatures, and that's what I've shown there. However, it's a balance between how old a lava flow is and how hot it started out. So if you have multiple sets of data, we can start placing constraints on what the composition of the lava that might be on Venus as well is. So this is very much work in progress. What we're trying to do, at least for the next few steps, are instead of just thinking about 1D temperature profiles, we're looking at using actual physics-based models of lava flow and placement on Venus, and using results from that model to compute what the radiothermal emission would be for flows of different ages and different starting compositions. And we're also looking into seeing if something like this would work on Earth. So we're basically using terrestrial radiometry data from SMAP and the AMSR mission, and doing something very similar to what Shannon McKenzie and Ralph Lawrence did in 2020 to find out if something like this would work on Earth. And the idea ultimately is to figure out, if we end up seeing something cool in the radiometry data, how do we actually interpret that and use that to then think about what the type and age of flows that might be on Venus's surface are. And I'm going to shamelessly plug my AGU talk here. I will be talking more about this at AGU on Thursday in the Venus session. So if any of you are planning to go and want to hear more, please stop by. Okay, and then in the last couple of minutes, I just wanted to talk a little bit about future directions, right? Sort of the things that we need to keep doing, keep pushing the field forward. Of course, we need more data. And we do have missions that are going to Venus, and we're going to have much better data than we had from Magellan, not just through SAR. The Da Vinci probe that I talked about will listen through the atmosphere and get photos of the surface. We'll take atmospheric compositional measurements. So we're going to definitely get a lot more data and a lot better data than we already have. But it would also really help to have actual in situ measurements from the surface, right? And there are mission concepts in development, maybe not going to be realized in the next decade. So it'll probably, we're probably going to be looking at least 30 or 40 years before something like this can happen and we get data back. So at least for the time being, synthetic aperture radar still remain our best way of studying Venus. But also some of these are programmatic decisions, right? These missions might launch, these missions might not launch, they might take longer than we expect. So what can we as a community keep doing in the meantime to keep progressing when it comes to volcanology? There are plenty of things we can do, starting with experimental work. So I talked a little bit about explosive volcanism and basaltic magma. And it's not something we understand very well, even on Earth. We don't understand how basaltic magma fragmentation happens. We don't understand how explosivity happens with basaltic magma. And that's something we can study through analog experiments. I also talked a little bit about unusual minerals on Venus's surface. And we don't have a thorough understanding of the dielectric properties of minerals at Venus temperature and conditions at multiple frequencies as well. So that's something we need to do better at. And also for a lot of these granular type flows on Venus's surface, we all, again, don't have a good understanding of how these flows work at high temperature and pressure. So sort of flume experiments towards that would help. And of course, we need more theoretical modeling, not just thinking about radar wave interactions in geologic medium, but also more physical volcanology models to better understand what eruptions onto Venus surface at high temperature and pressure might look like. And then finally, of course, lots of analog studies. So like I mentioned, at least for the next few years to a decade, we're primarily looking at synthetic aperture radar as our best tool for studying Venus. So looking at more SAR data of terrestrial eruptions and trying to understand those better in SAR data would help. and also analog studies, be it for seafloor volcanism or subaerial volcanism, characterizing activity levels on Earth better in both these settings, and using that to understand Venus better would also help. And finally, this is my last slide. I just want to finish by saying that all of these different activities, they're not just useful for thinking about Venus, right? Of course, we're trying to study Venus. We're trying to understand why this is different from Earth. But it's not just for understanding Venus, right? It has a lot more applications. For instance, for people that are studying exoplanets, for all the exo-Venuses and the exo-Earths that we're discovering and trying to understand, this is the type of science that would also really benefit the exoplanetary community. And also just for, looking back and thinking about our own planet, these are the types of studies that can help us better understand not just volcanism on Venus, but volcanism in a variety of different settings on Earth, including basaltic settings, intraplate settings, and seafloor settings. So I'm not just trying to push Venus science here. I'm just trying to say that this is broadly applicable to a variety of communities. And with that, I want to say thank you and finish my talk. And I have my contact information up there if anyone wants to reach out. I am actively looking for people to work with, including students and postdocs. So if you are interested, or if you know anyone that would be interested in the coming year, and if any of those topics listed above interests you, please feel free to reach out. Thank you.
Thank you very much. That was super interesting. And so do we have any questions in the audience? Duncan was first.
Yeah, great talk. Thanks for that. So those the very low emissivity regions tend to be higher altitude, as I understand.
Yes.
So is there an altitude correlation with the distribution of these pyroclastic deposits?
That's a really interesting question. For the most part, yes, right? So far there's been only, I want to say 6 or 7 deposits that have been found, and all of them except for one are present at high altitudes.
Thank you.
Thank you. It was a really good talk. So your possible pyroclastic flows are massive, and you're saying that the weird density is because of welding. So do you expect a variation in density across these big pyroclastic flows because the edges will be cooler? And do you have the resolution to observe that?
No, that's a really good point. And yes, ideally we would expect density differences across the whole deposit, and also just because they're tens of kilometers long, right? It's only natural to expect that. But the way we did this was we kind of took the average scattering property instead of looking at more localized properties across different parts of the deposit, just because some of these are really small that if we did that, we're especially for the emissivity data, what I should have mentioned is the emissivity footprint is about, depending on where you're looking at the surface, about 30 to 80 kilometers big. So, so when you're looking at emissivity data specifically, it does not make sense to divide that deposit up, like you said, because it doesn't have that resolution. But if we did have, but for the SAR data, that is definitely doable. But with just because we added in that emissivity in our modeling, it's not something we ended up doing.
Thank you very much. Can I throw it that far?
Thanks very much. So you said the change in slope between Earth and Venus will affect the sort of how far the pyroclastic flow runs out, but how does the atmosphere affect that, and also how does that affect like how far the plume rises before collapsing and things like that?
Yeah, that is a super interesting question, right? And that's one of the reasons. I'll start with the second part of the question first, and then I'll go on to the first part. So one of the reasons I said it's hard to get high energy eruptions on Venus is because the high pressure of the atmosphere suppresses a lot of volatile-like solution. So typically when you're erupting material out, just because there's not a lot of volatiles that have come out of the magma yet, it ends up being a smaller velocity and a smaller energy eruption than we would expect on Earth. So in that case, it's really hard to keep sustaining a column. And that's one of the reasons why a lot of these studies propose that they form by pyroclastic flows as opposed to by ashfall deposits, because having a sustained column on Venus is really difficult because of the pressure as well as the density contrast with the atmosphere. as for the second part of the question, how does the atmosphere affect it? So the way we model these flows, the atmosphere is, the pressure is somewhat of a moot point. It's not a big thing. It's not an important factor there. And I will tell you why. That's because we model these as similar to being very high solid particle concentration flows, similar to granular flows, or similar to debris flows that we would find on Earth. So in this case, the density of the flow, just because of having nearly 40% of solids in it, is super high that it doesn't matter if the atmospheric density is 1 or 75. But something I didn't go into is a lot of the pyroclastic flows we see on Earth are also dilute flows. They only have 1 to 2% particle concentration, right? And they travel as density currents. And that's when the density starts becoming important. So whatever advantage the flow can have over the atmosphere then dictates runout. For a flow, for a density current, or a flow that's going to be denser than the atmosphere, it's going to keep flowing. But once it's sedimenting particles out and becomes lower in density and equilibrates with the atmospheric density, that's probably where it's going to stop. So for those kind of density currents, and not for these type of high particle concentration flows, then the atmosphere becomes a really important point, but not for these ones. But that's something we started doing, did not finish, then I left grad school. So yeah, it's kind of hanging there.
Yeah, thank you.
Hi, awesome talk. I got 2 questions. First, I have a question about what the effect of exotic lava compositions like carbonatites or other strange silicic-rich lavas, how that would affect the way the pyroclastic flows behave. And then my second question would be about could the interferometric capabilities of Envision and Veritas pick up like ground inflation from magma moving, and does that help?
Yeah, great questions. So regarding the composition, I've not really thought about carbonatites, right? But I have thought about more silicic magma compositions. And, that would work really well in terms of having a lot more water. So typically silicic magma can hold more water in it than basaltic magma. So for really large explosive eruptions, you would expect that to be more common in silicic magma. So, if that is something that's common on Venus, more common than at least we think now, then it's possible that these deposits might also represent something that was erupted out of a lot of water in silicic magma as opposed to basaltic magma. But then that also poses a problem for the permittivity values that we're seeing, because we're seeing higher density, which is more typical of basaltic magma and not silicic magma. So having silicic magma would make life easier to explain some things, so then it would make life more difficult to explain some other things. And for the interferometric capabilities, so at the moment, the way interferometry has been planned is that Veritas will carry out pre-planned measurements over only 12 different orbit tracks, which is a bummer. And that's because I think they don't have I'm not a part of the Veritas team, so I could be wrong here, but I believe that's because they're not downloading native single look complexes everywhere. And there are only a few places they could do that for, and they've chosen 12 orbits. And I think it'll ultimately be up to the science team to decide what those 12 orbits are. And Envision might not do interferometry at all. Apparently, the orbit spacing is not right to have the right baseline for doing interferometry, and what we might end up getting is just opportunistic interferometry. So yeah, that would be really cool, having a that'd be cool if like the interferometric capabilities were better, but at least for these 2 missions, that's kind of where things are at now.
Thank you. Okay.
Has anyone actually been like hurt in this process?
We've knocked over a coffee before, but other than that. Yeah, that's true. That did happen. Great talk. I guess I'm curious about there's been a lot of debates in comparisons between volcaniclastic processes and the breccias made in impacts, or impactoclastic, if you will. Where people have tried to say a swavite is the same as an ignimbrite in texture and process. I'm curious if there's an opportunity with what you've done to compare to to the impact breccias right next door, do you see a big difference, or do they look more like similar processes, or definitively they don't?
I've definitely thought about that. So there's a lot of long impact crater flows on Venus that, again, some people have suggested might be in place more like lava flows, and some people might have suggested maybe more in place like clastic flows. In terms of the morphology, they don't look very similar to these. These kind of look like, these look very diffuse, whereas if you look at the impact crater flows on Venus, they have very well-defined margins. So they look more like lava flows, at least in terms of the morphology. But that's definitely one of those places something like this could find application in. And I think the and also that would actually be a better place for applying a model like this. Those flows have a lot of definition in the interior. If you look at these flows, they have levees, they show channels, which is common in both. They're definitely common in lava flows, but sometimes you can also get that in granular flows. So that would be a better place to actually apply some modeling like this for.
All right, I hope I get this right. So Prosenjit Ghosh asks, and there's a bit to unpack here. He asks about the residence time of pyroclast in the atmosphere. And do you have any idea about cratering having any relationship with volcanism? Is there any compositional variability between, of channel deposits compared to pyroclastics? And then he's also asking about the possibility of carbonatite volcanism. There's a lot of words there that I don't really understand.
Okay, let me try to remember this. As for the residence time of, that's a good, I actually do not know. I don't know much about the residence time of pyroclasts in the atmosphere. It's probably not very long, since these are not sustained column eruptions, but whether these are immediately going to go into a PDC when they come out, or if they are going to form a short column and entrain some air and stay in the atmosphere for a little bit and then collapse. I think they're both possible, but I don't have a good sense for what that timeline would be. Could you repeat the second part of that question, or like the latter half of that question?
Let's see, compositional variability of channel deposits compared to pyroclastics.
We don't, I would say we currently don't have the right type of tool to be able to say that, right? I think we can stand here and keep guessing about, are these mafic, are these more evolved? But we really just don't have the right type of measurements. We really badly need geochemistry from the surface to be able to put a lot of this into bigger picture context. Thank you.
More question? Yeah.
Also, I wanted to correct something that I said before quickly. Nicholas, for your question, I realized I was primarily thinking of repeat pass interferometry. So when I said the 12 orbits that Veritas will do interferometry for is repeat pass, or those were for repeat pass. For topography, there will be single pass interferometry across the planet. My bad.
You mentioned the altitude of the deposits, but what about the relief? Because some of the very big silicic volcanic fields on Earth are associated with intraplate rifting and have very comparatively low relief and multiple centers that coalesce rather than just one source.
Is there an example that you're thinking of specifically?
The Chonaki field in the far South Atlantic, Jurassic.
I'm not very familiar as much. When I was thinking of large silicic eruptions, I was thinking more about things that you would find in the Southwest, things like in Nevada and California, like the Valles Caldera. So the setting that you're talking about is not something that I am super familiar with.
I'll pass on some references you might be interested in.
Yeah, thank you.
Okay, I think we're good for the questions. Like just 11:30. Thank you again, Indujaa, for the seminar. And at 11:45, there is a lunch with students coordinated by Nicholas, and the meeting point is going to be, so in 15 minutes, down into the lobby where the comfortable leather sofas are, okay? And from there, Nicolas will lead you to a restaurant. There's also a dinner if you want to join this evening at 6:30 at Hop Dodi. You have all the information on the spreadsheet that you should have on the email. Okay, thank you. Have a good Friday.